am Floriane Magera, so I am innovation engineer at EBS Broadcast Equipment, and I'm also a PhD candidate at the University of Liège. So I'm going to explain you the camera calibration challenge that we've organized with the SoccerNet team. But first, what is the motivation for this challenge? So EBS is a world leader in live production equipment. So if you're watching a soccer game on television, you're seeing something that is using EBS products. So currently, the insertion of graphics in augmented reality is trending, and this is a subject of interest to EBS for that. And camera calibration is a way to bring AR graphics automatically in sports content. So this is why we organize this challenge. So I'm going to talk about the challenge itself. So I'll make quite an overview of it. Then we'll talk about the dataset. And as you will see, the challenge is divided into tasks. So the first task is the pitch localization, and the second task is the camera calibration itself. So for each of the tasks, I will talk about its definition, the baseline that we provide for each of the tasks, and then the evaluation method. So why is the challenge split into tasks? Because calibrating a camera from an image is challenging. Usually we use checkboard patterns or null patterns in order to do it. And so in the wild is a bit complicated, but in sports content, luckily, there is often a pitch whose dimensions are known and that can be used as a calibration target. So this is why we introduce the localization of the soccer pitch elements in the image as a first task, in order to lead to the second one, which is the camera calibration. So these are the two tasks. So the soccer pitch elements are the soccer pitch markings and the goalposts, and you have to localize them in the image. And then the second task is the camera calibration. About the dataset, so there are about 22,000 images that are annotated with polylines. So there are several points annotated on each soccer pitch markings and on the goalposts. So for the circles, there are as many points as necessary in order to follow the curvature of the circle. And for the lines, there are only two ends. But sometimes there is a few points more, maybe to follow radial distortion, I think. So for the first task, there are 26 soccer pitch elements. So there are 20 lines or circle arcs, and there are 6 lines belonging to the goalposts. Each element will be defined by its 2 extremities, and this is why we do not detect the localization of the center circle, because we cannot define 2 extremities for it. So given an image, we expect to receive a JSON file containing each of the soccer pitch elements detected in the image. So each of them has a class, and its 2 extremities here, X and Y, in relative coordinates. So I'm going to explain the baseline. So here I've made some code that I will share on the GitHub later. So first, a cell to download the dataset, so it's really easy. And then we are going to choose a random image. So this is where this is quite risky, because this is the baseline, so it's not working that well. So what do we have as an image? Okay, so I think the baseline will give correct results on this image. And so the idea here is to detect the extremities of each line present in this image. There are two kinds of extremities that can appear in an image. So the natural extremities of the line as in the 3D model of the pitch. So for instance, the corner is the end of the top line. And there is also the, how to say, not natural end of the line, which is its intersection with the image side. So in order to deal with these two types of extremities, we solve this problem as first a segmentation problem. So we trained a neural network that performs semantic segmentation. I chose a classic architecture that is a deep lab v3, and I trained it on SoccerNet dataset in order to produce segmentation maps. Okay. I have to take my mouse. No, oh, it's freezing. No, that's a problem with live demos. I have an old computer. Okay, it's loading the neural network weights. And now maybe I can analyze the image. So it's running on my laptop. If you've seen, my laptop is already freezing, so it's maybe a bit slow. Okay, we have it. So you see the segmentation mask here, and each color corresponds to the class of the soccer pitch element. You can see that you have some false positives here and there, so we'll have to discard them. And in order to extract two extremities from such a big amount of pixels, we decided to synthesize the blobs, the soccer pitch segmentation blobs, by fitting as many circles as we could on each blob. So with an image, it's much simpler. Okay, so you see all the circles that are fitted on the segmentation maps. And then maybe, well, we don't see here, but sometimes there are false positives of the same class. So there might be a bit of the top line here. And we have to account also for that. So once that we have all circles, we'll link them in order to create polylines as were to generate the same kind of information as were annotated. And we are going to generate for each class a list of polylines. And we will return as extremities the two ends of the longest polyline. So that's what's in the next cell. And as you can see, the results are there. It's not very precise. But we can work with that to perform camera calibration. So I will compare that to the annotations themselves. So as you can see, so the annotations are the void circles. So sometimes we are close to it, but we're not very precise. So the baseline is not very good. And there is also, once that you run the baseline on the whole test set, you can evaluate it, you can compare it to the ground truth and obtain quickly the results. And so we reach an accuracy of 21%. So now I'll explain a bit more this accuracy. So we have pixel precise annotations, but I'm not sure that we can say that there is only one pixel in the image that could represent the extremity of each line. So in order to account for this ambiguity, we defined a threshold and we compute the distance between a predicted extremity and the corresponding annotation. And if the distance is smaller than a threshold t, then we'll say that the extremity is correctly detected. So this is a way to frame our problem as a detection task. So as you can see here in the example, we have a ground truth here and a prediction in blue there will be considered as a true positive. And if we predict an extremity here, it will be farther than t pixels away from the ground truth. So it would be a false positive. So using this thresholding strategy, we can use an accuracy metric. So for each of the extremities predicted, we look in the polylines annotation in order to find the extremity that is associated with the same class. If there's a question, or no? Okay. Thought so. If there is no matching polyline in the annotation, the extremity is a false positive. If there is a matching polyline, then if one of the extremities of the polyline is closer than t pixel to the prediction, is a true positive, as a false positive. And if there is a polyline that isn't present in the prediction, then we'll count both its extremities as false negative. And so this defines our accuracy at t pixels. And we'll use a combination of the accuracies at 5 pixel, 10 pixel, and 20 pixels in order to evaluate the winner of the challenge. So this is the current leaderboard status. So you see that there are currently 3 submissions, 3 public ones. So the current scoring isn't the final one, because here I think that we score by accuracy at 10, and the final metric will combine the 3 of them. Because of course it's more interesting for us to have a better accuracy at 5 than a better accuracy at 10. And the winner will get a prize of $500. Okay, so that was for the first task. Now, the second task. So given an image and given the 3D soccer pitch model that is defined by the FIFA rules of the game, we ask you to provide the internal and external camera parameters following the pinhole model. And optionally, you can also provide distortion parameters. For each image, we expect to receive a JSON file containing the position of the camera in meters, its orientation, the focal length, principal point, and radar distortion. Okay, so first, we have a 3D model. So I put a virtual camera 60 meters above the pitch, above the center of the pitch. And we see this is the 3D dimensions of the soccer pitch that we would see if we had a camera in the air at 60 meters. We define also our reference axis systems. So in a soccer production, most of the cameras are on the same side of the pitch. And this side of the pitch is so the x-axis is directed towards the right goal. The y-axis is directed towards us, and the z-axis is oriented towards the center of the Earth. So we've seen that we weren't very precise with our detection of the extremities, and we first see the type of line that we get when you use them. So it's not very good. I'm afraid, but maybe we can have a camera calibration with those lines. So what I do here is that I compute the line equations based on the extremity detection, and I match each of the line with the line equation of the model in 3D. Then we are going to leverage the fact that the soccer pitch is a plane, and we are going to express the transformation applied by the camera as an homography, because the homographies can capture the projective transformation of 2D planes. So we are really using the fact that the 3D pitch is a plane. And we are going to try to estimate the homography. It works, but this is not very expressive. So we'll see if we project the 3D soccer pitch model in the image, what kind of drawing of the lines do we get? That's okay. That's not perfect, but I think it's quite coherent with the scene. And then using the fact that we are looking at a plane again, and a plane located at the z equals 0, we'll extract camera parameters from the homography. And it's not very precise, but we can see that we have quite a consistent position. This is a view of a main camera, so a camera located on the middle line, at the level of the middle line of the pitch. We are 10 meters above the ground, so this is consistent too. And we do not estimate any distortion. And we can use the SoccerNet PIP package in order to estimate the camera calibration results once that we've applied the baseline on all the test sets. So this takes quite some time, but previously we had 28% of accuracy. So I'm going to explain more about the accuracy itself now. We use the same annotation for the camera parameters evaluation. So we only have the polylines annotations. So there is no ground truth for the camera parameters. So there might be several set of camera parameters that provide the same results on an image. That's not a problem for us. It could be a problem in other applications. So we use an indirect estimation of the quality of the camera parameters by using the projection of the pitch model in the image. So we are going to sample the pitch model in 3D. So we'll generate a lot of 3D points, and we are going to project each of these points in the image. This will give us 2D polylines in the image. And so to have a picture of that, we are going to frame this as a threshold. We are going to use a threshold in order to frame this as a detection task again. So in blue, we have the annotated points that can be in any configuration. That's why they're not spaced evenly. And then there is the projected polyline that we obtain by using the camera parameters provided and the 3D pitch model. So we are going to consider each soccer pitch element and ask ourselves if the soccer pitch element is correctly detected. And we'll consider that a soccer pitch element is correctly detected if all the points belonging to the annotations are closer to the polyline, the projected polyline, than a certain threshold. So for each of the annotated points, we are going to look around it with a circle of t pixels. And if the polyline is closer than t pixel, we say, okay, this point is correctly matched with the polyline. And then we do that for each of the annotated points. And if all the annotated points are closer than t pixels to the polyline, then we say that the soccer pitch element is correctly detected. Okay. Then, this allows us again to frame the detection, the task as a detection, and we'll consider each polyline, and if there is no matching polyline in the annotation, we have a false positive. If there is a match in the annotations, then we use the matching strategy that I just explained in order to make the difference between a true positive and a false positive. And if there is a polyline annotation that is missing in the projections, then we have once false negative. And this is how we frame this with an accuracy at t pixels threshold again. Okay, so, but the problem, as I said with your question, Silvio, is that we need camera parameters. So if there is no camera parameters provided, we cannot evaluate. So we provide another metric, which is the completeness rate, which is the number of images that are correctly calibrated divided by the number of images in the challenge set. And of course, we do not check the camera parameters quality. So if you have to choose between providing camera parameters or not providing them, maybe not provide them if you're not sure about the quality of your camera parameters. Okay. And for the leaderboard, it's quite empty right now, so don't be shy. There is a $500 to win. Yeah. So that's it for me. I don't know if you have questions.